Good. It's a very great pleasure to be here with those of you here in person and for those of you online. As was just indicated, I'm going to be speaking 3 times today, and my objective in this overall series of presentations is to introduce concepts to those of you new in the field, to present some of the latest developments, but there are also limitations. Although I'll be speaking for the best part of 3 hours, I would really need several days to cover the topic. And so what I'll be presenting is not complete. It's to give you some idea of what are some of the issues, but I do encourage you to read more. And it is your responsibility to decide what is useful and what isn't. And I acknowledge at the outset, there are many important topics I simply don't have time to address. So we're going to be looking at the application of liners in mining applications. And these include lagoons, which contain waste liquids, processed water, and potentially marginally contaminated stormwater. We're going to look at them as bottom liners for heap leach pads and tailings storage facilities. And they're used as covers for tailings storage facilities and waste rock piles. And these can be quite significant structures, both in aerial extent and in the thickness of waste that we're dealing with. There are 3 fundamental questions that I'll be addressing. The first in this lecture are what are barrier systems and how do I select the right liner for a given application? In fact, that second part follows through all 3 lectures. We'll be looking at the types and applications in particular in this first lecture. The next question is how much will they leak? And we'll be looking at 6 relatively simple equations that can be used to calculate leakage in different environments. The real key is picking the right equation for the right application. And then we're going to deal with the question of how long will they last? And what is the service life? So we'll be taking quite a journey. And I want to put this all in context of environmentally sustainable mining. As you're probably all aware, we're seeing a massive increase in the demand for minerals worldwide. Much of it is due to electric cars. And the purpose of electric cars is a more sustainable environment. But we can only achieve that if not only we have the electric cars, but we have sustainable mining to get what we need for those electric cars. And sustainable mining requires, in particular, protection of both surface and groundwaters from contamination, both during operations and subsequently. So providing adequate groundwater protection has a cost. And in fact, if you go for the cheapest solution, you're probably wasting your money. If you're going to do it, you might as well do it right. And doing it right is not cheap. And that means we have to accept the fact that it's going to cost us more as consumers at the end of the day. So to do the protection we're talking about, we're going to require barrier systems. There are many different forms of barrier systems. I'm going to be focusing on those relevant to the climate in Canada and in Helsinki and Finland. So we'll not be talking about deserts where you might be dealing with different approaches. The individual components that we'll be talking about all have finite service lives. And that means we need to consider what is the finite service life and design a system that can be maintained in perpetuity, because that's what we're talking about. So let's begin with some applications. We've got ponds, frequently found in mining applications, 2 here at one particular mine in Canada. And we have to deal with holes in liners, as you see here and here. These ones are over voids due to differential settlement in the subgrade beneath the liner and ice loadings. These due to bears. And we have to remember that exposed geomembranes are exposed to many possible mechanisms for getting holes. Tailing storage facilities are another major application, not just in the dam, but in the containment facility itself. Heap leach pads. Here, they were early adopters of geomembranes because of the economic advantage of collecting as much as practical of the pregnant liquor. But there are also environmental advantages to collecting it. Then final covers are a critical component of mine facilities. And they have multiple components. This is one particular example shown here with foundation, geomembrane, a sand protection layer, a physical barrier and drain, and a SAM loam cover. They can be more or less sophisticated than that. So there are a number of materials that we consider when we're talking about liners. In the geomembrane world, we think of high-density polyethylene, linear low-density polyethylene, bituminous geomembranes as 3 of the more common ones. Then we have geosynthetic clay liners and compacted clay liners. So there's a range of products in each of these categories, and there is a great danger of thinking of black plastic as simply a single commodity, or thinking of as a GCL as a single commodity. There are, as I will try and demonstrate to you, many variants, and they're not equal. So we have to recognize that when we're talking about HDPE, there can be as much difference between one HDPE and product and another as there is between one linear low and another. And in fact, there can be more similarity between a good quality HDPE and a good quality LLDPE. So they say a cover doesn't tell you about the book. A name doesn't really tell you very much about the product. So if we look at a barrier system, the sort of materials that we might encounter include gravel as a drainage layer. If we're going to have a geomembrane, then gravel and geomembranes don't get on well. And so we have to keep them separated by some form of protection layer. Geomembranes, the most common, are 1.5 to 2.5 millimeter thick HDPE. And here we see a GCL, a geosynthetic clay liner, coming on a roll. It's a layer of bentonite, a natural clay, which is sandwiched between, in this case, 2 geotextiles and held together by needle punching. And we can use these materials together as part of a composite liner. A geomembrane and GCL works together much more effectively than either material alone. We can have a compacted clay if we've got suitable material, and we can use that together with a geomembrane. And of course, we can use a clay compacted, a GCL, and a geomembrane. So let's look at the type of barrier systems we could be dealing with. Starting with the very simplest, we have ponds. And our objective in a pond is to minimize the movements of fluids, liquids, and sometimes gases from the pond. We may also be trying to minimize evaporation in some applications. Then we come to waste piles, where we're trying to minimize the escape of contaminated waters to the groundwater and the surface water system, both through the bottom liner, but also in the lower parts of slopes. And we are going to be trying to limit the ingress of liquid, generally water, but also sometimes oxygen into the waste pile. So we have your traditional HDPE, we have linear low density polyethylene, we have bituminous geomembranes, and in all of those cases, they are essentially impermeable. The leakage through the intact material is effectively negligible. We'll come to how they do leak in a moment, but let's contrast those three liners with a geosynthetic clay liner, which is not impermeable. It has a quite finite permeability, and we can calculate the leakage as being related to the hydraulic conductivity and inversely related to the thickness. And of course, the same applies to a compacted clay liner. So we have the first three, which are impermeable if intact, and the last two, which do allow some leakage. But although I said they're impermeable, all liners leak. And those impermeable liners leak because it's practically impossible to build them with zero holes. And as soon as we have a hole, we have leakage. And here we see three examples we looked at before. Two of them in ponds caused by ice loading in winter. You get a bit of wind behind that ice. It creates quite a lot of pressure on a geomembrane. If you combine that with differential settlement, you get what you see here. Wildlife, bears, caribou, elk, reindeer, kangaroos, leopards, all will do nasty things to an exposed liner if they get in. BGMs are often sold as being very robust. Be very careful in believing that. Here are examples of significant holes in BGMs. No liner is robust enough to survive poor construction. Geosynthetic clay liners, if not properly looked after, can shrink, leaving a gap. Compacted clay desiccates. There is nothing that is perfect. We need to recognize that and design to mitigate against it. So all liners leak, and they leak through holes, and that's affected by, of course, the area of the hole. It's affected by the head, the height of fluid trying to escape. It's affected by the material adjacent to the liner, and that can play an important role, as I will show you. We need to recognize that we also may need a protection layer for the liner. We need to take account of what is adjacent to the hole and how that will resist leakage. We may need a drainage system, and that drainage system can control the head above the liner, reducing the driving force. So we have here in the bottom right-hand side the single composite liners that we typically see. In one case, we have a drainage layer. And we may go to a double line system where the primary liner is going to have the major leakage. And by putting a drainage layer below it, we can collect the majority of that leakage. But the primary reason for that drainage layer is to reduce the head on the secondary liner. So yes, we will collect what escapes or what we can of it, but its primary purpose is to reduce the driving force through the secondary liner. And whenever we have two or more components, we have a barrier system. And a barrier system often involves components that work together synergistically a geomembrane and clay liner, for example, and antagonistically, a drainage layer of gravel and a geomembrane have to be kept separated. And rarely do we ever use a material that doesn't have a weakness. And our design objective is to mitigate those weaknesses. So, this greatest long-term and short-term risk when you have a geomembrane is holes. And those holes can occur during construction, immediately after construction, and during operations. Those that occur during construction can be minimized by good design and good quality control and quality assurance. So that is something we can control. If we have an exposed geomembrane, it's also exposed to the weather, it's exposed to animals, and there we have to take proactive measures to minimize the damage that can occur. We can get problems because of differential settlement, and we get problems because of the nature of the materials above and below the geomembrane, particularly when we have applied pressures. So we could have a situation where we had no holes when we built our heap leach pad or built our tailings storage facility, but holes occur because of what's in the subgrade and the loadings that are applied. So we have to recognize that even if we build it with no holes, that doesn't mean it's going to remain with no holes. So how many holes can we expect? Typically 2.5 to 10 holes is what is used in design. Typically there are about 3 holes after initial installation. And then when we put a cover soil on top of it, that increases to about 12 holes. In this presentation, I'm going to assume generally 5 holes per hectare. And a median hole is about 5.6 millimeters in radius. So to minimize holes in a geomembrane, we need high quality construction, quality assurance, and look for the holes. So there are various techniques when you have an exposed geomembrane. The puddle method we see here can be used to find holes greater than about 1 millimeter, sometimes even smaller. And we can do it with geomembranes that have a conductive backing. We can do with a geomembrane on a moist GCL, or we can put in a layer of material that is used to allow for spark testing. So that conductive film there is very thin, and it's simply there to allow detection of holes in the overlying, in this case, PVC geomembrane. And here we see the process, and the hole gets found and fixed. Then we go and use heavy equipment to place soil on top, and that's when more damage occurs. But we can also do a dipole survey to identify the presence of holes. We need to think about that at the design stage and early in construction. And the installation contractor has to work closely with the people who are going to do the electrical leak location survey in order to get good sensitivity. But even with good sensitivity, we're probably going to miss holes 5 millimeters or smaller. So there is a limit to what we can achieve with finding holes, despite our best intents. And we've got to recognize that and design for that. Here is an example where there are over 20 holes per hectare at the time the leak detection survey was done. Obviously, they fixed that 20 holes, but that doesn't mean we're at 0. It means we're at 20 less than we would have been otherwise. And what are the greatest targets for damage? Wrinkles. When you have polyethylene and you place it, it's nice and flat. It expands when it gets hot. If you cover it when it's got those wrinkles that come from the expansion, they get locked in. And the process of covering it with typically a bulldozer means you've got a blade happy to cut through 1.5 to 2.5 millimeters of plastic, as you see here. And here is a hole. And these are BGMs. This was a large mining application where BGMs were sold on the basis that you didn't have to worry about your subgrade, you didn't have to worry about what you would put on top of it. They were very robust. And they decided to do or the owner decided to do a leak location survey and found 39 holes per hectare, ranging in size from 5 to 150 millimeters in diameter. That is 20 to 18,000 millimeters squared. The next year, they knew there was going to be a leak location survey, and there was still 18.4 holes per hectare. So BGMs might be thicker than HDPE, but they're just as prone to getting damaged. Now, BGMs don't wrinkle. That's one of their selling points. But they get holes just as readily. And then there's post-construction. And this is particularly relevant to things like heap leach pads, where you have drainage layers in close proximity to the geomembrane, and you have, in some cases, very significant loadings, which can both, in the short term, create holes. In the longer term, they create tensile stresses, and those tensile stresses then become stress cracks or holes. And here we see one particular heap leach application, the geomembrane, with some relatively steep slopes, the ore, and the pond where geomembranes are also used. So if we look at the holes that we get post-construction, they're related in particular to just isolated stones in a finer grain subgrade. It's actually worse to have a few isolated stones than a whole layer of gravel. Puncture is more likely the more gap graded the soil is. And even if there's no puncture, you can develop large tensile strains that ultimately become holes. And it turns out it's the shape of the grading curve that's more important than the maximum particle size. So if we want to design an appropriate barrier system to protect the environment, we need to answer a number of questions. Firstly, we need to look at its geologic and hydrogeologic environment and ask what are the geotechnical and hydrogeological site conditions. What is being contained is an important consideration in deciding what is the barrier system. How much leakage or fluid escape is acceptable? If it's fresh water, the amount you can allow to leak could be 100,000 litres per hectare per day. If it's a highly contaminated water, it could be less than a litre per day. How long must that containment system last? What is its design life? And what is the environment in which it must function? And how can that change during its design life? Finally, when we think we've got a good design, we've got to sit back and ask ourselves what could go wrong? And what are the unintended consequences of this design? Many failures occur because people don't ask those questions. There have been quite regular failures of tailings storage, leak leach pads, mine waste piles, ponds and lagoons. The more dramatic ones get reported in the press, but far more of them are actually occurring than you probably hear about. And when those failures do occur, it's rarely for unforeseeable reasons, but rather related to inadequate investigation, inadequate design and or construction, and it's often caused or triggered by excess water, which can often be a result of inappropriate operations. Geosynthetics are relatively new to the mine waste management and historically have been predominantly used either in ponds or heap leach pads. There have been a lot of successful applications of geosynthetics. You tend to hear about, again, what doesn't work. They do work extremely well, but they are engineered materials and they need to be treated with the same respect as other engineered materials. A civil engineer graduates usually with a good training, several courses in reinforced concrete design, and with 0 courses in designing with geosynthetics. So when they fail, it's often because the material specified was substituted for a cheaper material. When people say they're equivalent, be very skeptical. What's on the specification sheet doesn't tell you about equivalence. Often failures occur because the engineer didn't really understand the material that they were using when they specified it. They gave little or no consideration to what's happening between the time it's placed and the time it goes into service. And a good design can fail because of what happens between the time it was installed and the time it went into operation. So it's good in the sense it's good if you could wish it into place. But it's bad because they didn't think about how do I design so it actually lasts until I need to use it. Inadequate construction, quality control and assurance is a common cause of problems. So many different products are available. Salespeople can be very helpful, but you also have to check their claims very carefully. Some are responsible, some are just interested in a sale. Some of them know what they're talking about. Some of them have no idea what they're talking about. And remember, the salesperson isn't responsible for the design. It's the engineer. They should be the people asking the questions. A lot of engineers rely on warranties. A manufacturer warranties this for 40 years. It's next to meaningless. Firstly, if you read the fine print, it's usually prorated. Secondly, it's only for material replacement. And usually that is only a small part of the overall cost. So relying on a warranty is not going to help you very much. Another common mistake is people specify the wrong thing. They want it cheap, and sometimes a supplier will recognize it's going to be a problem and actually give you a better product than you paid for. But as soon as you start relying on that, you're in trouble. Good engineering can be relied on. Luck is fickle. So, also be wary when people get up and say, oh, it doesn't leak. I was at a hearing recently where an engineer for a project in Canada's North got up and said, we're going to build this cover, we're going to use the geomembrane, and it doesn't leak. And so my question was, how do you know it doesn't leak? He said, well, we've monitored these. You know, we put them in a pond and monitored it for days, 2 days, and we couldn't measure the leakage. I said, what was your measurement? Oh, we could measure it to within 20 millimeters. That's 200,000 litres per hectare per day that they couldn't detect. When they say they don't leak, be very skeptical. Begin by asking the question when you're in design, what are my options? There are many possible systems and materials. You need to know what are your alternatives. And you need to know how much leakage is acceptable. You need to know how long it has to last. And here in mining, one of the problems is the people saying they want this facility say it's only got to work for 50 years. And then they discover there's more minerals there. And a frequent question I'm being asked was, well, we designed this for 50 years. Can we get 100 years out of it? If you design it for 50 years, chances are you won't get 100 years out of it. If you designed it for 100 years in the first place, then you might be able to get it. So be realistic in estimating how long it's going to be required. Ask yourself, what's the environment in which it must function, and how can that change during the design life? So we need to think of the many options. All liners have strengths and weaknesses, and you need to understand both. And I'll be talking about both. Be very enthusiastic salespeople. And remember, if you really want containment, you need more than one line of defense. So we commonly consider these materials. I've mentioned them already. And there are a range of products within each of those categories. And I will point out to you that they do not behave the same. There can be as big a difference between one HDP and another than there is between an HDP and an LDPE. Know the strengths and weaknesses of both, and I'll be touching upon them in all three lectures. Design for reality. Consider what will happen through the entire lifetime of the system you're designing. And particularly what can happen between installation and full operations. You must have a robust system. So, polyethylene. It comes as a chain of carbons with hydrogens. And which category we put it in depends on the branching. HDPE is a very linear structure, whereas LDPE is a very, very branched structure. Now, what's the significance of that? Well, firstly, what we call HDPE today is not really HDPE. It's usually a medium density resin because we found that HDPE was too prone to stress cracking. And so most of the geomembranes produced today have a medium density with better stress crack resistance. In some cases, they're being blended with LLDPE. The advantage of that is lower crystallinity, and that gives you improved stress crack resistance. Today, you can get products with a minimum of 500 hours stress crack, in some cases over 10,000 hours. I don't have time to go into it in any great detail today, but the number the manufacturer tells you is a fiction. It's not the real material property. It is the property that comes from a test conducted immediately after manufacture. It is a product of the materials and the residual stresses built up in manufacture. And what you really need to know is what is the true stress crack resistance, which we can obtain, but it takes at least 90 days of testing 90 days of aging before you do your stress crack test. As I say, we don't have time to get into that, but I want to draw your attention to it. So a geomembrane must withstand the temperatures it is going to work with. So you need to understand the temperatures. You have to understand what chemistry it's going to be interacting with. And typical drinking water is relatively benign. Distilled water is not. Chlorinated, highly chlorinated water is not. So even water has to be looked at for its chemical compatibility. So if you need a service life greater than 100 years, if you need to deal with temperatures that are elevated, if you need to contain water that is distilled or chlorinated, or in any other way contaminated, then you need a higher performance geomembrane than what is the traditional commodity geomembrane. And you need testing to verify that it's suitable for your application. So this applies to virtually all mining applications, the exception being control of stormwater. Now, it's very easy to think that I have a piece of black plastic and I have another piece of black plastic and they're the same thickness. They're the same. They look at the spec sheet. They both meet GRI GM 13, a international standard. They're black, smooth, non-conductive, but they're not the same in most cases. We have to consider how they're going to be affected by exposure conditions and temperature, and how that interacts with the formulation. And for one piece of black plastic, you can have at least 150 different ways of formulating it. That means you've got potentially 150 different service lives because of difference in resin, difference in the chemical additives added to the resin, differences in the carbon black that's added, and the differences in special production additives. And when you look at all those variables, as I said, I gave up counting at 150. And that's just for the black smooth plastic. And we now have far more than just a black smooth plastic. We have textured, one side, two sides, or no sides. We've got white. We've got a white textured with a smooth edge. And then we add conductive to that. That same black core has 14 possible variants, 14 possible different service lives, and they're not all the same. So you need to think about what is it that I need for my design situation, and how is that particular product going to perform? Then there's the question of HDPE versus LLDPE. LLDPE is perceived to have a much greater flexibility than HDPE. That's largely an incorrect perception because it's often made comparing thinner LLDPE to thicker HDPE. HDPE is cheaper. If you compare apples to apples, it is true that LLDPE is a little bit more flexible, but not massively so. There is a lot of variability within the LLDPE family, just as there is within the HDPE. The important thing is not the label. The important thing is what's under that label. What is the resin, and does it have adequate real as against perceived stress crack resistance, and does it have an adequate antioxidant and stabilizer package to protect it in the long term? Those are the two important characteristics. Specification sheets will list things like this. All very interesting, but really doesn't tell you anything. And this, and this. And you can see there's a bigger difference between smooth and textured, whether it's LLDPE or HDPE, than there is between the LLDPE and the HDPE. And none of those parameters are actually relevant to design. So let's look at the parameters that are relevant to design. And one of those is the standard OAT. It's a test we can do that picks up some of the antioxidants that are in the geomembrane. And other things being equal, if other things ever are equal, other things being equal, a little bit more is often better than less. Although there are many issues, and this is one of them, that I consider a Goldilocks problem. Goldilocks in the fairy tale didn't like her porridge too hot, and she didn't like it too cold. She liked it just right. And that's what we need to do in selecting these materials. So here we have 4 different products with a range in standard OAT. And there's another test, HPO2, with a different range of products. Then we've got stress crack resistance, 720 to 19,000. Break strength, break strain. How can you tell which of those is going to be adequate and best for your situation? And the answer is, you can't. All of that table tells you very little about how it's going to perform. We're going to come back to that in the third lecture. Bituminous geomembranes have been grossly oversold because of some things that are true and some that are not. They don't wrinkle, that's true. They are thick compared to HDPE, that's true. They're less likely to be damaged, that's not true. They're easier to seam, that's true, but as we'll see later, not very good. And they've been successfully used, and this is quite true, for decades for containing potable water. But remember that potable water, if it were to escape at even 100,000 litres per hectare per day, it's a minor concern. You can get that much evaporation. But when we've got a contaminated site, we have to worry about how much is leaking. And there we have to be much more careful. I will again come back to bituminous geomembranes, but let me just say at this point, caveat emptor, buyer beware. I want to finish off with GCLs. They come in two forms, one with adhesive holding the bentonite to a structure, and 95% or more are a layer of bentonite sandwiched between two geotextiles and needle punched together, as we see here. They're produced with a carrier geotextile, the bentonite being placed to cover geotextile, and then they're needle punched. Some of them are heated to get the fibers that were needle punched melted and adhering, and that is important. Since needles can break off, you also need a metal scan to detect them. Now, when I just talk about a layer of bentonite between two geotextiles, it sounds like it's one uniform material, but it's not. That bentonite can vary. Its particle size can vary. Its geotextiles can vary, and they can have a profound influence. So here we see one particular GCL. You can see its different components. This one has a woven carrier. You see the needle punch fibers. Here is another one. You can see here we've pulled it apart, so you can see the woven carrier, the needle punch cover. This one looks very similar at this point, but it's actually got a scrim reinforced non-woven. If we pull it apart, we can see in the bottom, the non-woven and a woven have been needle punched together. That is an important detail. Then the thermal treatment. So here are three different GCLs. The third one I haven't talked about yet has a polyolefin coating. It's a plastic layer that's applied molten during the manufacture and gets impregnated into the carrier geotextile. So there are a wide variety of GCLs, and they will perform differently, as we're going to see. This is a case where we've got a plastic layer that is not as well bonded as we saw in the previous examples to the carrier geotextile. Some of these are laminated, it's glued on. And it makes a difference whether it's glued or laminated or whether it's been applied in a molten state. And coated GCLs can be used with the coating up or with the coating down, depending on what is the problem you're trying to solve. The mass of bentonite is an important consideration. If you want it cheap, you buy less bentonite, but the bentonite actually plays an important role and is variable. So how much bentonite you use makes a difference. So we've got a whole range of things that look the same on a specification sheet, but you've got differences that are subtle, as you'll see, very important. So moisture uptake by a GCL is going to depend on many factors. It's going to depend on the way in which the GCL is manufactured. It's going to depend upon the soil it's in contact with. And it's important because it influences something called cation exchange and interaction with leachate, which affects its hydraulic conductivity, its ability to contain hydrocarbons, gases, the likelihood of panel shrinkage. And we need to understand all of those factors. So they depend on many factors. Let me illustrate the differences you can see, depending on method of construction. So we're going to look at 4 GCLs, and we're going to start with a non-woven, and let it to hydrate until it doesn't want any more water. And here's a histogram, and you can see the scatter, which is the variability in the product, from a single roll, and you can see that it's around 190% water content. This is from the same manufacturer, but with a woven carrier, and you can see that that makes a difference to the statistical distribution of water contents, with an average of around 210. This is scrim reinforced and thermally treated, and it's hydrated about 125%. And this is a woven, thermally treated, very similar to number 3, except for the thermal treatment. And you can see that makes a difference. Now, this is how much water it needs to be hydrated. And a common assumption is that my GCL will be hydrated in the field. Well, it may or it may not be. Let's put it on a subgrade with 16% water content. We take 3 of those GCLs, and we plot moisture versus time. And you can see they've hydrated to about 100 to 120% gravimetric. Well, if we look at that, you can say GCL4 is the most hydrated. It's got the highest water content. And GCL2's got the lowest. But it actually isn't the water content that matters. It's the degree of saturation. And we plot the same data as degree of saturation. We see a very different story. You can see the one that only needs 125% to be fully hydrated is at over 80% degree of saturation. The other one is at about 50%. And that will affect its long-term performance. So the product, the water content of the subgrade, the nature of the subgrade, are all going to affect how it hydrates. So the following statements are true under ideal conditions, but mostly false in the field. The first statement is the form of the bentonite, whether it's powdered, fine granular, or coarse granular, doesn't matter, since they all have the same K when hydrated. That is true in the index test used for the specification sheet. It is virtually never true in reality. The closest you get to it is a pond with clean water. But it is generally a false statement. How GCL is manufactured will not affect its performance, since it's the bentonite that controls K. Again, only true under ideal conditions, rarely true in practice. And a GCL will be hydrated to the point of near saturation from the subgrade and will have adequate hydraulic high conductivity. True under ideal situations. In practice, G cells are usually around 50 to 60% degree of saturation. So I think I will pause at that point.